we start with a subject that we left off the other day, and that's the Moonies and the Loonies. Who are the Moonies? Moonies are the people who believe we never went to the moon, and humans never stepped on the moon. And we're not going to deal with them today. And who are the Loonies? People we will deal with today. The Loonies are people who say or think or believe that the moon spins. And we're going to set them straight today. Okay? So let's begin with them. But where do we begin? Well, we must begin with definitions. That's where science begins, at definitions. You have to get the keywords straight before you can talk intelligently. We have to be on the same page in order for you to understand the mechanism that I'm going to convey to you. Okay, so that's the issue. Okay, so let's begin with a definition. The first definition is the word definition. We have to define what a definition is. What is a scientific definition? That's where we start. Okay, and there you see it. It's a limitation placed on the extent of a usage of a word. Okay, I always give the example. Rotten example, really. It's a lousy example, but I think it drives home the point to most people out there, and that is that, I can say it's big, it's white, and it's got wings. And what am I talking about? Am I talking about Big Bird or the White House? And after, I keep adding things like, it's a building, it's got columns, etc. President lives there, then, you're talking about not Big Bird, but the White House. Okay, so that's more or less what we're referring to here. Okay, a scientific definition is rational if it can be used consistently throughout your dissertation, okay, or throughout your group's theories, right? If one guy uses one definition, the other guy in your same religion, your same congregation uses a different definition, well, we might have a little bit of a problem, okay? Definition is not equal to meaning. Definition is what the prosecutor spits out, and meaning is what the jury receives, okay? Meaning is on the receiving end, so you cannot use the word meaning to define the word definition. That's the point. They are not synonyms, okay? But in ordinary speech, people use these words interchangeably. They don't even know what they're saying. In science, we have to be very careful, okay? And you'll see why today, especially. Concepts we define, objects we point to. You don't define chair. You don't define table. You don't define rock. You don't define tree or dog. You point to them so that the Klingon, who just came to your planet to visit you, understands or learns your language, your nouns. So you point, name, say, like Adam probably did, God put him there. You had to name all the animals, so, you point and name. That's the way it's done in physics, okay? And the object has to be a standalone object. I always make a point of that because people miss that, and that's a very important one. It can't be a dependent object. You cannot say halo, that a halo is an object. And I'll tell you why. Because, you need the angel. See, all you have is really a ring or a plate there. That's it. But a halo is a holy ring, a holy plate. And the only way you're going to get it to be holy is to put the angel in there. So the halo is, in that sense, is a dependent object. It needs the angel in order for you to call it a halo. Otherwise, it's just a ring or a plate. And the same with in physics. You can't bring a magnetic field, standalone magnetic field, and put it in the middle of the conference. You need to bring the magnet with it. Or, the earth, if you're going to talk about a gravitational field. So no, field is not a physical object, not a standalone physical object. Okay, so people treat it as a concept, as an object, and it's really a concept. And again, it's a dependent object, and that turns it automatically into a concept. Okay. Anyways, only strategic words are defined. We don't define every word in the dictionary. People say, Bill, you say that an object is that which has shape. Yeah. And they say, well, what do you mean by shape? Well, first of all, it's funny that you did not ask me, what did you mean by that? Or by which? Or by has? I mean, is it easier to define that than shape? I challenge you. I mean, you can even look it up in the dictionary. You probably won't understand the definition in there. But it's much harder to define those words. But anyways, the point is we don't define every word in the dictionary to please the devil's advocate. Okay, we define only those words that are necessary. And why don't we define shape? Because we don't need to define shape. All we need to define is the word object, and an object, right now we have a definition from the mathematical establishment, and they treat it, whether they define it that way or not, because they have many definitions. They define it as that which has volume, that which has mass, that which moves, that which can be used as a subject of a sentence. They have all these definitions, but the primary one that they use is see and touch. And so they say an object is that which you can see and touch. And so all we are doing here is saying, look, you got the wrong criterion or criteria. An object is that which has shape for the purposes of physics, not that which you can see and touch. Not all objects can be seen or touched, especially the table that the Klingon has on the other side of the planet of the universe. Okay, you can't touch that one or see it. Does that mean that table is not an object because you can't see or touch it? Besides, it's subjective, whereas shape is not. An object has shape even if it's the only object in the universe that God made, or the devil, whoever. Okay, so operational and functional definitions, they're out. They're unscientific. We don't use those. That's again, a custom of mathematics that they say, oh, this is an operational definition. It's a functional definition. So they give you their whole dissertation, and at the end of it, they say, okay, this is what I meant by that word. That's how they define words. They define it through an experiment, like the result of an experiment and so on. No, that's an unscientific definition. So we don't use operational or functional definitions either. Okay, moving on here. So what's the issue? The issue is the word spin. People say, does the moon spin? Does the moon not spin? And people have no idea. Mathematics, the religion of mathematics has taught them that the moon spins. Why does the moon spin? They say, well, because it rotates around the earth in 27 days. And throughout that time, it takes one turn completely around. And so they're saying it does spin. It doesn't spin like a top. It takes 27 days to spin, but it turns one complete time around its axis. That's the logic. That's or you could call it illogic. And why is that? Because they haven't defined spin. So what is the word spin according to mathematics, according to our current thought out there, ordinary speech? Okay, here you have it. I pulled it out the other day. I'm going to go quickly. Spin to turn around an axis. That's all they say. That's quite straightforward. Okay, some people put some more adjectives in there, but that's the essence of it. And you look at the synonyms: rotate, gyrate, to circle, to twirl, whirl, spiral, etc. And pretty much people use these words interchangeably. The problem is when you get to the bottom right there where you see orbit. Is the orbit the same thing as spin? That's the question we're going to analyze. Is there a difference between orbit and spin? And some people are not quite sure. And let me show you one case here. A fellow wrote, and he says, my understanding is that the moon does not rotate around its axis. Does it rotate around the Earth's axis? This is a very interesting question. It is an important question. And in order to address that issue, well, we need to know what that word spin means. Okay? And so, yeah, the moon he accepts that it doesn't spin around its own axis, but it says, does it spin around the Earth's axis? For this, we have to define the word spin scientifically so that we get rid of the definitions of mathematics. Okay, so let's define this word scientifically so that we're all on the same page. It doesn't mean you have to agree. If you don't like the definition, you have only one recourse, and that's to come up with your own definition, get inside the ring with shield and sword, and defend it. That's the way it works in science. It doesn't say, well, all my buddies, they voted for my definition. No, we don't care about democracy. We don't care about tradition. We don't care what you've used always. We care about what you can defend in the ring. Okay, so get in the ring with your shield and sword and defend your definition. Okay, here's my definition. Okay, spin, 3D. Okay, I pulled this out the other day so you can look at the previous video and get more in depth on it. But the point here is circular motion of an object's surface around what? Its fixed axis. The axis has to be fixed. If the axis turns with the object, with the thing that you're analyzing and the thing that you're saying is spinning, right? If it turns with the axis at the same rate, it's not spinning. Okay, so that's the bottom line. Now, people say, well, Bill, you're crazy. What do you mean? An axis is one-dimensional. So now we're going to get into the nitty-gritty. We're going to show these people where they're mistaken. They have been misled. Okay, so let's get to the nitty-gritty. Okay, here we have, here we have a few more issues. So let's put them all together here. One fellow says, what do you mean by stating the moon rotates together with its axis, but the Earth does not rotate with its axis? How does something not rotate with its axis? So he's putting his finger on the right problem. Okay, this is the problem. People don't understand what's happening here. And there I'm showing you a little axis. It's a three-dimensional axis. Okay, and I color-coded it so that you can see something, right? Again, it's just for the sake of understanding. Okay, And you can see the one on the left, that's the correct one. The axis turns together with the moon. Okay, so there's, it's always, the moon doesn't change its location. The surface, any point on the surface of the moon is not changing its location, its distance or anything with respect to any point on the axis there. It could both rotate at the same time. So it always maintains that distance, that, that separation, whatever. On the other hand, the one on the right is wrong. That's not how the moon twirls. Okay? It doesn't twirl that way, because if the axis is standing still, then any point you have on the surface changes its location with respect to whatever point you want on that axis. Okay? So this is a 3D notion. Okay? We're going to start with that. We're going to go slow here, okay, so that people understand. We're not here to make you believe. We're here to make you understand. That's all we're interested in. Okay, and the fellow continues. He says, discussing whether or not an axis co-rotates is misleading. These types of axes are, for our purposes, one way or the other, merely theoretical concepts. Very interesting point, okay? With no real life application, no actual rod at the center of any celestial body that I know of in the first place. Okay, so he says, I guess I'm not allowed to put a rod in there to make my case, he's saying, because there is no real rod in the center of the earth or the moon, for that matter. And so to talk about the twirling of the rod or not, or the rod standing still while the surface of the moon rotates with respect to the rod, well, he says it's too abstract, or not real, or it's misconceived. Okay, that's what he's saying. Okay, we hold on to that point. Here's another fellow, and he puts a comment. He says, if the moon was the seat of a swing, okay, and the earth was the bar on which it swings on, and the swing did a 360 degree rotation of the bar, the earth in this case, right, standing for the earth, then the seat, moon, does not spin. And so the issue here is that guy spinning, or is he orbiting? Well, all we have to do is, as long as you stick to the definition, I promise not to hurt you. Right? How do we teach in the bgaede School of Physics? We teach with a baseball bat. And I can't use a baseball bat here because it's too long, so I use my dough roller. I hope you don't mind. Okay, it does the same damage. Okay, so is this guy spinning or is he rotating? Well, you got to spin with respect to your own axis. Okay, and that axis doesn't belong to the guy. Okay. So he is orbiting. He is not spinning. We use this in ordinary speech and say, oh, he's spinning, he's spiraling, etc., rotating. We separate two words only, spin and orbit. He is orbiting. He is not spinning, according to the definition. Okay? So just clarifying that, which is an interesting point. And here we have, I think, flat earther. Okay? We do have our flat earthers here. If I can find, oh, here it is. I got to show this always, okay? Here we have the flat earther. And what does this flat earther say? He says, I believe in Freemason Hollywood productions. Nice computer animation, referring to one of my videos in the past. Any real findings? Any real footage? And yeah, the problem here is people think that this is a question of see touch. They say, can I see footage, an actual footage? Well, usually the problem with flat earthers is that even if you show them a footage, real footage, they say, well, that was made in Hollywood. That wasn't out there. Because if we went to the moon, or even into outer space somewhere, or even send a probe out there without a human, right? Well, that probe can take a picture or film the Earth or the moon from afar, and you say, well, it's round and it's spinning. I mean, you could do it just by looking. And so they have to deny that we went to the moon, that we went to outer space, etc. Fine. The way we do it in science, we don't go out there, because we can't all go out there and verify with our eyes and hands or whatever. The way we do it, we stay here on Earth and we use our brains. Okay, and what we do is conceptualize, so we don't need to see. Okay, the way we do it in science, we cut off our hands and we close our eyes. Okay, that's the way we do it. That's the way we start. And once you do that, you're safe, because now you're going to use your brain to visualize. Okay, what's going on out there. And of course, a flat earther, what he's got to do is explain gravity. Okay, and if he can't explain gravity, which they can't, not in a rational way, well, they're dead. They're dead in the water. Okay, so where do we start with this spinning thingy? Well, we start with a gentleman. His name was Hermann Weyl. Weil in German. He was a German guy. And Weyl, he was a mathematician. He was a contemporary of Albert Einstein. Okay. In fact, they were almost, they died in the same year. They were almost born in the same year. Einstein was, I think, like 6 years older than him. And so they lived pretty much together in, throughout the same period of time. And while Whale, um, he was a fan of Einstein. He was a relativist, and he wrote a book, Space Time Matter, okay, where he analyzed Einstein's theory. And he was a friend of Einstein. He was also a friend of Schrodinger, by the way. A little more friendlier with his wife. He slept with Schrodinger's wife while Schrodinger slept with some other wife. And if you would have confronted them, they would have said it's relative. It's all relative, and that's how the theory of relativity got popularized. Everybody wanted to do relativity. Okay, yeah. And so, what does Mr. Whale say or do? Well, here it is. This is from his book, okay, Space-Time Matter, and he starts by laying the foundations for this geometric theory known as general relativity. And so he says the following, which takes us to the subject matter of today, which is the axis. Okay, so to every point P of S, there corresponds one definite homologous point P of S, which after the above displacement to a new position, and that's the one I want you to focus on, displacement to a new position, right, would be surrounded by exactly the same part of the given content as that which surrounded P originally. We shall call this transformation a congruent transformation. Okay. He defines what a rigid body is. He says we mean one which, however it be moved or treated, can always be made to appear the same to us as before, if we take up the appropriate position with respect to it. And there he has a big error, and it's the big error of mathematics, and that is that they introduce an observer, which makes it subjective. We can't use this definition in science. Sorry, Mr. Weil, whatever. And so he can't use this definition because he's introducing an observer. He says it's got to do with how you see something. So if one guy is drunk, another one has shot up with cocaine, and the other guy, is upside down, well, they're all going to see something different. Okay, so what are we talking about? Okay, so no, that's not what a rigid body is. But let's continue here. It's just important in the sense that he's saying that it's got to do with distance. All particles comprising a body have to be at the same distance when you move it, and he's going to call that a rigid body. So he defines a straight line, and this is where we get into the axis region. Okay, its distinguishing feature is that it is determined by two of its points. Okay, thus if A and B are two different points, the straight line includes every point. And he continues on there, okay, and then he says the straight line lies evenly between its points, expressed kinematically, meaning with motion, right? This is tantamount to saying that we regard the straight line as an axis of rotation. So what's the problem? The first problem here that we have with Mr. Well's definition, which is the one we have inherited all the way to Mr. Euclid, is that they never tell you what a line is. Is a line a row of apples, or is a line the rolling of one apple down the street? Is motion a line? Is an itinerary a line? And this is where we run into trouble with mathematics, because mathematics treats them all as synonyms. From a physical point of view, the motion of one object is not the same thing as an object that is stretched, a bubble gum that is stretched, okay, or many apples or whatever. Okay, so here we have a little bit of problem. Okay, especially when Mr. Whale is going to construct his line with points, and he says his line is one-dimensional and his points are zero-dimensional. So he's constructing his one-dimensional line with zero-dimensional points, and I'm not smart enough. I can't visualize either one of those. Okay, that's going to be part of the problem here. Okay? I guess the problem is with me, right? Okay. So he continues, okay, and he says, we may say that the straight line is derived from a point by an infinite repetition of the same infinitesimal translation in its inverse. A plane, however, is derived by translating one straight line along another. In the case of rotation, for example, the points on the axis are distinguished by the property that they preserve their positions. In other words, if you're going to rotate something, the important thing is these positions, these distances with respect to that axis. That's what the notion that people have today of what spin is, what rotation is. And here I've illustrated essentially what Mr. Whale says about both the point and the line. Okay, this is how he constructs his line. First of all, this is the point, constructing the line. Okay, so he says that a line is something that is the motion, a translation of a point. Okay, that's what he's going to define, even though he says a line is defined by 2 points. And then he says that it includes all the points in between, all the apples in between. What is he talking about? Is he talking about points or locations? Is he talking about positions? Position is a concept. A point, meaning a dot, right, is an object. So the reason all these people can't define the word point or line is that what they're doing is they're mixing concepts with objects. The dot is an object. The position is a concept, and what they have is the dot position, and they say that they call that a point. And you say, well, which one is the point? Is the point the dot, or is it the location? Which one is it? And that's where they run into trouble because they illustrate it with a dot and they call it a point. And they say it's zero dimensional, even though a position is non-dimensional. You can't talk about the location or position of a concept, and the dot is two-dimensional. So with that, they construct a non-dimensional point. Okay, he doesn't stop there. He says, how do you construct a plane? Well, you take that same line, and now you're going to move it downwards. And now you're going to paint or you're going to scan a plane. Okay, this is how Mr. Whale, especially not only him, I mean, everyone since the days of Euclid has been doing the same thing. They've been scanning these geometric figures and constructing objects of higher dimensions. Okay, so this is where we start. Okay, what's the problem with all this? Why has everyone from Euclid, even before Euclid was a student, I guess, of Aristotle there, because if you look at the time frame, we don't know exactly much about Euclid, but he probably lived in Athens first, studied in Athens. At the time, you had the the Lyceum of Aristotle, and then he came to Alexandria, not Virginia, but Egypt, and that's apparently where he spent the rest of his life. But yeah, since the days of Euclid all the way to today, okay, what have all these people been doing? Well, they've been using Euclid. They've been doing the same type of geometry. They've been scanning things and constructing higher dimensional objects by scanning, by moving objects, by translations. Okay, so what's the problem with all this? Well, let me tell you what the problem is. If Whale is right, if you want to look at spin, you got to look at if the object is changing its distance with respect to the axis, some axis in the center. Okay, so if something moves completely in a perfect circle, right, around an axis, the axis is one-dimensional, right? The object has to maintain the same distance no matter where. And let's assume the moon does that, for example, with respect to the axis of the Earth, okay? Then yes, you can say that the moon is spinning around the axis of the Earth, which is one of the questions that a fellow asked there. What's the problem? In physics, there is no such thing as one-dimensional object. There's no such thing as a zero-dimensional object. There's no such thing as a four-dimensional object. There are only two types of objects, and they are 2D and 3D. Okay? And so there is no 0D, no 1D axis. Okay? Especially the 1D. No 1D axis. There you see the 1D axis. That's what it looks like nothing. What are you going to put? Because as soon as you make it a little wider, you got the 2D. That's the problem. So those two belong, 2D and 3D, those belong to physics. You can talk about those. You can't talk about a 1D axis in physics. Only in mathematics, in the religion of mathematics, can you use the 1D axis, the notion, this concept, okay? And we're going to be talking about spin. You can't talk about spin with respect to concepts. 1D line, as they call it, is a concept. And again, we don't know if it's a bunch of apples or an itinerary, okay? But for this purposes, they say, well, it's a bunch of apples. You have all these apples, all these points, one right after another, and they build a line, and we're going to hold them still so that you can maintain your distance with respect to each one of those points. That's the notion they have. But the problem is there is no 1D or in physics. And if you're going to talk about spinning, especially about the spinning of the moon or the spinning of Earth, you better talk in three-dimensional terms. Okay? So just bear with me a second here. I'm just going to go through this. You reach your own conclusion. Okay? We're going to start here, okay? We're going to get rid of these two other axes, okay? Three other. There was the four-dimensional one as well. Didn't touch that one. Not important, okay? And I'm going to color code them a little bit, okay? There it is. And the color coding is just so that I can show you visually, what's going on here, okay? Again, all this is just for the purposes of understanding the theory, the concept behind the argument that I'm going to present today, okay? Okay, so we have this 2D and a 3D barber pole there. Okay, what are we going to do? We're going to draw a circle around their bases. Okay, so there's a circle around the 2D plane. Okay, this elongated rectangle. Okay, that's what it is. That's what you're staring at. Objective. It's whatever you stare at. That's what it is in physics. There's no, no run around. We don't talk about energy. We don't talk about fields because nobody knows what those are. No, we show you what it is. We're talking about a plane. Okay, that's what it is. Two-dimensional plane. That's all you got there. Okay, you're staring at it face forward, right? And we're going to draw a circle around it. There you have it 2D. We color-coded it red and blue. And now we're going to put in that environment a ball. Okay, so we have a ball in there now. Okay, and what are we going to do with this ball? Well, as you can see by the green circle, we're going to run it around. We're going to go around that thing. We're going to find out if the distances change. Okay, so let's measure the distances. And again, we don't need to have numbers here. All we need to know is separation, the distance of physics, not the distance of mathematics. Distance of mathematics is distance traveled, and it's measured in meters, seconds, if you do it with a clock, right? But it's measured in meters, it's measured in feet, inches, those are the units we use. That's not what distance is in physics. In physics, it's separation. We do not have to have units or numbers. Okay, so what are we going to do with the ball? Well, we're going to measure, okay? And again, we don't need numbers. All we need to know is that one stick is longer than the other, okay? You can see that the distance between the green ball, the surface of the green ball, and the red edge there is longer than the one on the inside edge, okay, which is the blue one there, or a bluish one. And so what happens? Let's move the ball. Okay, we're going to move the ball now. Okay, there it is. So has the distance changed? And we're going to hold the plane fixed, right? We're going to hold that axis. We're going to hold it fixed. And the question is, has the distance changed from where it was before? Okay, and we're going to move it some more just so that you get the hang of it. Okay, here we're going to move it to the other side. If I can get this thing in there. There it is. Okay, has the distance changed? Is the distance changing from the ball to the edges of this plane? Okay, and I'm saying that the distance changes. The separation between the ball and each one of those edges of that plane is changing. From a conceptual point of view, I think you understand that we don't have a congruent transformation, as Mr. Whale would say. The distances are changing. Okay. And so something is happening here. Now, if that plane, assuming, right, rotated together with the ball, the distance would remain. But if you fix that plane and just move the ball, the distances are changing. Okay, so I want you to understand that. Let's do it with a pole so that we can get into the habit of understanding. Okay, here's the pole. Okay, so we have the ball. We're going to look at the distances, the separation between the surface of the ball and each one of the edges of that barber pole. Okay. And we're going to move the ball now, okay? And has the distance changed with respect to the edges of that pole? And the answer is yes, I think. I think people would agree with me that it looks like the distances are changing. And here, again, moves to the other side. Okay, hopefully you can see that the distances are changing. You don't have to follow me. You can do this at home in the presence of a relativist always. It's a dangerous experiment, okay? And you can figure out, you can do it with a string. You can tie a string around a pole, find out if the distance changes, okay? If the string gets shorter or longer, like if you tape it to the edge of the barber pole. Okay, so the distance changes if you use 2D or 3D. Okay, that's the point I'm trying to make there. Let's do it with respect to the 1D now. Here's the 1D. That's what it looks like. So has the distance changed with respect to the 1D? Well, the issue is that the 1D, we cannot illustrate it. So it's not that I'm being funny here. It's that I have nothing to show you. I cannot illustrate the 1D for you. Okay? That's the problem. And so when they put a 1D artificially in the religion of mathematics, they are sticking a physical object in there. They're insinuating that stick is a 1D stick, right, is a physical object. And they're going to be establishing distances with respect to that so-called axis. That's what they call it. And so, yeah, you cannot even imagine the twirling, the rotating, the spinning of the axis itself because it's one-dimensional. What's there to spin? You don't even have an object. That's what the 1D looks like. If you're going to talk about spin, you had better use at least a 2D, more likely a 3D object. You have to stick an axis that has some length, width, and height inside the Earth, inside or through the Earth and through the moon in order to talk about spin. And it better stand still in the case of the moon. I'm sorry, in the case of the Earth, and it better move together with the surface of the moon in the case of the moon. Now you might say, there's another twist here, okay? And let's go with that one. And you might say, well, Bill, what if I use the edge of the plane? Okay, there you have your one-dimensional, your one dimension. Okay, so you're going to use the edge. What's the problem here? You can say the edge is always one dimensional. Well, is it? How thick is your edge? Where are you going to take the reading? Say, well, right at the very edge of the edge. Well, are you going to use the mathematical point, the location, the dot that is two-dimensional? Please illustrate it for me. Illustrate the edge without the without the elongated square rectangle there. That's what you got to do. If you can't illustrate the edge all by itself, then you don't know what you're talking about. Because all you're saying is you're trying to get away with the edge, but you can't tell me how thick, how wide that edge is. So what is the problem? The problem is that all these people have been using the word axis, which has nothing to do with physics, has to do with what they call a mathematical object. I guess that's how they would describe it or define it. And what they're doing is cheating. They're doing is cheating because what's happening? What they're doing is saying they never worried about rotating the axis itself. So they say we just check distance between the axis and the ball that's going around. And of course, since the axis is one-dimensional, has no physicality whatsoever because it's a concept, it's even worse than that. It's a bunch of zero-dimensional points, one stacked on top of each other. And so we have no idea what this axis is, okay? Because you can't draw it. You can't use it as a physical object. You cannot say it belongs to physics. And what they do is they hold it steady, and they say, we just got to change your position, as they call it, with respect to the axis. And so to them, it doesn't make any difference if the axis rotates or not because it's one-dimensional. But you can't do that in physics when you use 2D, if you want to do it with 2D like I did here, just for the purposes of illustration, or with a 3D actual object. If you're going to talk about spin, you're talking about a physical word that belongs to physics, doesn't belong to mathematics, okay, at all. And if you're going to spin, and talk about spin, and you're going to define it, you better define it with respect to a fixed axis. If the axis moves with you and the definition of spin is changing distances, change in separations, well, you won't have any change in separations if the stick moves together with the surface, if they both rotate at the same time. So yes, we need to know whether the axis spins or not, okay? And we can't use the axis of mathematics for two reasons. One, because it's not an object. Second, we cannot illustrate it. It doesn't belong to physics at all. Okay? And so that's the problem with the axis. So yeah, spin, you spin if your axis stands still, is fixed. And the surface spins with respect to that axis. If, like in the case of the moon, the axis spins together with the moon, you don't have spin. Okay? And all you have from the moon really is what is called an orbit, meaning the moon goes around the earth. It also goes around the fixed axis of the earth, okay? But it's not changing its location, assuming it were a perfect circle, right? It's not changing its location with respect to the center of that axis of the earth.